be used to measure the number of interactions between points on the two-dimensional plane. These interconnected diagrams are called networks. Oh, you mean like computer networks? Yes, like computer networks. The only reason that the computer networks would be completely insane if they didn't figure out new ways of doing things. Same with phone networks. Used to be phone networks work this way. But anyway, I'll get into that in a minute. How many sides and diagonals are there in a five-sided figure? So, if you think about a five-sided figure, you have the five sides, and then you'll have this one crossing to that one, this one crossing to that one. And then you'll have this one crossing to this one, and this one crossing to this one, and then you'll be left with one more, which is right there. Now that's for 5. So you have 5 sides and 5 diagonals would be equal to 10. But you can imagine just increase that to 8 or 9, and it becomes ridiculously hard to count. So we don't want to do that. But anyway, how many diagonals are there in a 5-sided figure? 5. There you go. Or sorry, how many sides and diagonals? 10. How many diagonals alone? 5. And it's not always exactly the same number, so watch out for that. Okay, I'll show you how to do it. So the sides and the diagonals can be thought of as connections or relationships. How many relationships are there between a group of 6 friends? 7 friends, 8 friends, 9 friends. So if you think about it, you've got a relationship here, and you got a relationship here, and here, and here, and here. So that's 1, 2, 3, 4, 5. And then you'd go, now when we say relationship, we're going to say it's a two-way street. So a relationship with Ann and Fred is the same as the relationship with Fred and Ann. It's a two-way connection. You don't have to count them differently. So if we go over to Eldon here, we could go 1, he's already got his connection to Ann, 2, 3, 4, so you'd add 4 more. Then you could go down to Deirdre here, and you could go Carolee, or sorry, we've already got Eldon, we've already got Ann, we don't have Fred, so 1, 2, 3 there. And then go to Carolee, you'd have Bob and Fred, which is 2. And then finally you'd end up with Bob, and you've already counted everything else. So 5 plus 4 plus 3 plus 2 would be 9 plus 3, which would be 12, plus 4 would be 14. Now, nobody's going to do this. So, if you think about it, it's like, how many different things you got here? You got 6 different ways, and since connections are like two-way streets, you're saying 6 different objects connected in 2 ways. 6 choose 2. What's that? 6 different. This is one of those memorizing things. You just got to memorize. This is the way to do it. 6 choose 2. And somewhere I must have missed. See, I got 5, 4, 3, 2. There was somewhere in there. It should have been a 1, and I obviously missed it. D, E, 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 E. Shoot. I missed it somewhere.
You missed Bob and Gary.
Here. Okay. Yeah, and that's my extra 1. So the answer should have been 15. Thank you. Anyway, who wants to ever do that again? Not me. So 6 objects can be connected, interconnected by way, two-way street connected, 2-way. So 6 choose 2, 15 from then. This is everything. Now, if I just wanted to do diagonals, this is all the diagonals. This is the sides and diagonals, right? Oh, sorry, I didn't finish the question. 6 friends, 7 friends, 7 choose 2, 8 friends, 8 choose 2. But now, if I ask the question, what about just diagonals? I just want to know how many diagonals there are. Well, if you know it's a 6-sided figure and there are 15 interconnections, then if you just wanted diagonals, what would you do? You'd go 15 minus 1, 2, 3, 4, 5, 6 sides, and you'd get 9 diagonals. Okay? So make sure you're answering the question correctly. So in a 7-sided figure, you'd have 7 choose 2 ways of interconnecting all the things, and if you wanted diagonals, you would subtract the 7 sides. So diagonals is equal to 7 choose 2 minus 7. Diagonals likewise would be here, would be 8 2 choose minus 8. Okay, now this is what I was trying to say. The telephones and computers are the same in that when they first were installed, they had to be directly connected to each other. Same with computers. And so the number of interconnections between telephones soon became astronomical because you have to go straight to this one, straight to that one, straight to the other one. So telephones were connected to a central switchboard, and that's why you had an operator, and the operator would physically connect you with a wire to the other person. They had a big pegboard, your number, somebody else's number, your number, and they would chunk it in there, and they'd chunk it in there, and then they would connect the two. And you can imagine if there was, 42 homes, all the different connections would have been there. Without the operator to do it would have been a real problem. So let's just ask that. How many direct interconnections would be necessary to connect 25 telephones together without a central operator? It would be 25 choose 2. Ouch. Huge number. And so operators are invented. Now this is the same thing happened with computers, and the way they solved computers is not by putting a central operator. When you go to the internet is basically connecting almost all the computers in the world that are together. They don't do it by an operator. What they do is, the reason why it's called internet is that your computer sits on the internet and it actually receives all the signals from all the other computers on your ISN, your service provider. So TELUS, if you're on TELUS or Rogers, your computer actually hears everything that's out there. And that's why it is dangerous. Other people can start to listen to your stuff. All they have to do is deconstruct the packets. Anyway, packets of information come to your computer with a header on them that says, this is for the IP address of a computer. Your computer reads that and rejects it. If it's not for me, it just doesn't even read it. If it has a header that has the IP address of your computer, then your computer accepts it and reads it. And of course, this is happening at the speed of light. So it's rejecting far more stuff than it ever picks up. But again, you can see the problem with that and how things get hacked. If all of that stuff is flying around, if you're sending out information to everybody else's computer and you want to send it only to the TD bank where you're banking, somebody could, in fact, intercept those things. And so they have moved to secure networks, which then what they do is they encrypt those packages. So even if somebody grabs the packet and steals it, which they can't, it's too hard for them to decode what the information is on there, so they can't get your credit information or whatever. But eventually people will hack that, and then you'll be in trouble again. And so then they'll come up with a new method, and that's why we're always getting updates, because somebody hacks the way we used to do it, they change it, and then somebody hacks it, and they change it, and so it's this dance between, stopping the hackers from hacking and all. Anyway, that's how it works. But it doesn't work like this anymore because it'd be too crazy. All right. Our study of combinatorics takes us to Pascal's Triangle, which is a really interesting triangle. There are different kind of things. There's Fibonacci sequence and stuff like this, Pascal's Triangle. Interesting things that people just thought of, and then you find out later that it actually has a substantial use. And Pascal's Triangle has a substantial use in combinatorics. You'd never believe it, but it does work. Well, what is Pascal's Triangle? Pascal's Triangle is this. You start with 1, and you write 1s down the side of Pascal's Triangle. It's just basically a pyramid of numbers. That's what Pascal's Triangle is. But the pyramid is created, each level below it is created from the level above it by taking the two numbers on either side and adding them together. So since that's a 1 and that's a 1, you take those two numbers and you add them together and you get 2. So then if I go down to the next one, I add these two numbers together to get 3. And then I add these two numbers together to get 3. And then I keep moving down, I get 4. You can imagine you're just going to keep adding 1. So basically these numbers just grow in a numeric sequence because you add 1 to each one. It's in the center that things start to get large because 3 plus 3 is 6, and 4 and 6 makes 10. And then, so it's the numbers in the middle that start to expand and get bigger and bigger and bigger fairly quickly, not super quickly. Well, it turns out that you can actually form Pascal's triangle using combinatorics, if you think of it this way. Now, here's the part that messes people up. You have to think of the first row of Pascal's triangle as row 0. If you think of the row 1 as row 0, then 0 choose 0 will give you 1. In row 1, you would have 1 choose 0, and then you'd count over 1 choose 1. And then in row 3, you'd have 3 choose 0, 3 choose 1, that's 3. 3 choose 2 is 3, 3 choose 3 is 1. Am I in the right place?
0, 0, 1.
Here, here, here. Yeah, there's row 2, there's row 3, here's row 4. Here's row 4, which is right there. No, sorry. No, that's not what I wanted to say. I shouldn't be saying row. I would say the leading number. You can see the leading number. Well, I guess I do call it row. So yeah, I'm doing this right. So the leading number is 4. So herein, I just missed 2. That's my problem. 1, 2, 3. That's better. There. That's why I was having so much trouble. So row 4 starts with 4. 4 choose 0 is 1. 4 choose 1 is 4. 4 choose 2 is 6. 4 choose 3 is 4, and 4 choose 4 is 1. Then this row is 5. So this is going to be 5 choose 0, 5 choose 1, 5 choose 2, 5 choose 3, 5 choose 4, 5 choose 5. And you just work your way across like that. So fill in the next row. I did that. Predict the center number in the 8th row. Okay, now the problem is you don't want to fill out the whole Pascal's triangle just to get some number in the 8th row, especially the center number. So what you think, okay, watch out for this now. If I said in the 8th row, but we count starting with 0, so the 8th row is really the what row? The 7 row, right? It starts with 7. Oops, you can't see that. Sorry about that. So the 8th row, because we start counting at 0, the 8th row is 8 minus 1 or 7. So the first number is 7 choose 1, and then it goes 7 choose 2, 7 choose 3, 7 choose 4, 7 choose 5, 7 choose 6, and 7 choose 7. Now it says center number. Now I wouldn't have had to write these all out, because what's the center number in 7 things? There are 7, sorry, I missed 7 choose 0. 7 choose 0, okay? Now, don't forget we're counting that 0. So 7 choose 0, 7 choose 1, 7 choose 2, 7 choose 2. Okay, in 7 things, starting with 0, there are how many things? 8. So 7 things, and count 0. 0, 1, 2, 3, 4, 5, 6, 7 is 8 things. So what's the center thing of 8 things? Well, Mr. Gasser, there is no center thing because there's 2 of them, right? So when I say center, you have to take 2. So what would be the center thing of 8 things? It'll be number 4, right? Number 4 would be the center of 8. But watch out, it's not number 4 because we started counting at 0. So it's actually number 3. It's the third. It's not the third thing in. It's the thing that has 7 choose 3. See? 7 choose 0, 7 choose 1, 7 choose 2, 7 choose 3. Now, since there's an even number, it's both of these. It's 7 choose 3 and it's 7 choose 4. But what do we know about the 2 numbers in a row that has an even number? What do you know about the 2 middle numbers? They're both the same. In the odd rows, you get a unique middle number. In an even row, you get an even, meaning even number of things in the row, you get a doubled number. So if you do all that thinking, you don't have to count out the number. The thing is going to be 7 choose 3. What is 7 choose 3? You can do that on your calculator. So now I could ask a question like, in the 21st row, what is the center number? Well, in the 21st row, you go 20, choose the center number. Well, in the 21st row, you would have 22 numbers stretched out, and the middle of that would be 11. So you'd have 20 choose 11. That's how you do it. But anyway, in this case, it's 7 choose 3, So 7, choose 3, and on my calculator, that gives me 35. Okay? Alright, so what practical purpose would Pascal's triangle have for us? Very interesting where Pascal's triangle shows up. You probably have done this and never noticed it before. Or maybe you have noticed it, just didn't know what to do with it. For example,
why is it 7 choose 3?
Why is it 7 choose 3? Okay, because in the 8th row, when you start counting at 0, your lead number is 7. Right? And in the 8th row, there would be 8 numbers in a row, which means the middle number would be 4 and 5. But you start counting the row at 0. So it's 0, 1, 2, 3. Now, because these two are equal, you could have said 7 choose 4. But the reason why I'm choosing the 3 is because when the rows are odd numbers, you do have to back off by 1. Right? If you said the middle is 5, it's not really 5, it's 4. Because you start count. This is I mentioned this a while ago. When you count from 0, you have to watch out. Because 0, we count 1, 2, 3, 4, 5. But if we count 0, if I say in 5 objects counting with 0, how many things are there? You always have to say 6. There's one more than there was before. So there's a little bit of one less. There's the one less idea, but there's also the one more idea because you start counting at 0. Which is wrong. If I started counting at 0, why was I subtracting 1? Wouldn't I be adding 1? In the 8th row would actually start with 9. Oh my gosh. That's terrible. Right? Wouldn't the 8th? Boy, I screwed that up. If the 8th row, if you look at there, this is the 4th row, it starts with 3. No, I was right the first time. Why am I saying that? Boy, don't make me ask. I answer no more questions. You mess me up when I answer questions. Okay, sorry. The 8th row starts with 7. But if you start counting across, starting with 7, you start at 0, and you end up at 7, which is 8 things wide. And then you would choose the middle, which is 4 things over, but starting at 0, you go 1, 2, 3, that's the 4th thing over. That's why I went 7 choose 3.
There's 2 in the middle. 7 choose 3.
Yeah, there's 2. These 2. But I'm going to, because there are times when it's odd, I want to make sure I pick the right one. Because when it's odd, there is only 1. It's because it's even. So there's 2. But the 2 are equal.
So I can pick either?
You can pick either one. Yeah, either one because they're both the same. All right, binomial theorem. What? Binomial theorem? You don't even know what I'm talking about. Oh, but you'll remember once I start doing this. Let's jump over here because this is more familiar to you. A plus B squared. If the teacher asked you to do A plus B squared, what would you do? You would go A plus B times A plus